SwayamPrabha. Digital India. Educated India.
Welcome to the course on micromachining. My email address is given over here for future contact by any of you. Here I will like to first make the acknowledgement from where some of the slides for this particular lecture have been taken. As you can see, a short term course on micromachining was organized by Bhabha Atomic Research Center and IIT Kanpur during October 7, 2008 to October 11, 2008 at IIT Kanpur. In that short term course, a lecture was delivered by Professor R. Balasubramanian from Bhabha Atomic Research Center, Mumbai. This also includes some part from a chapter on diamond turn machining written by Dr. R. Balasubramanian and Dr. V. K. Suri of Bhabha Atomic Research Center for the book on Introduction to Micromachining, which was edited by Dr. V. K. Jain and it was published by Narosa Publishing House, New Delhi, India. Now, the outlines of this particular lecture are as follow. First, I will give you the introduction to the diamond turn machining, and then certain definitions are there related to the diamond turn machining. Then we will see mechanics of micro nano machining in diamond turn machining, DTM, then design features of diamond turn machining machine, what are the various components of DTM machine, tool, and you require metrology file making the parts or the components on the DTM. We will discuss that, and I will give you some examples of the products that have been formed by DTM machine. Diamond turn machining, you can have different types of the machines for diamond turn machining, like 2-axis lathe machine which has X and Z axis or R and theta axis. You can have 3-axis lathe machine. You can also have 5-axis lathe machine which are normally called as machining center. The specialty of these machines is that different kind of operations can be performed on these machines without really changing the fixtures. Now, I will give you introduction to DTM, diamond turn machining machines, and some basic definitions. We will deal with nano machining. Normally DTM is used for nano machining and machining process capable of generating products with sub-micron form control, that is less than 1 micrometer or greater than 1 nanometer. You can have sub-micron size control on the dimensions, that is dimensional controls, and you can have few tenths of nanometer surface finish. This is very important because many applications, as we will see in this particular lecture, require surface finish of the product in nanometer or even sub nanometers, that is in terms of angstrom. And there are various ways of expressing the surface finish. You can use one of them just like RA, RQ, RY, and you will find different researchers and scientists are using different ways of expressing whether RA or RQ or RY. Even Some countries use RA while other countries may be using RQ and RY. So, most of the equipments which deal with surface finish, they give the surface roughness value in terms of RA, RQ, RY, all the three. So, that whichever is applicable you can make use of that, and then we will see what is unit material removal, and it is atomic clusters of materials. Now, finishing techniques are basically in two groups. One is known as soft loop finishing techniques. It is very important. In this particular technique, the tool and workpiece, all points are in contact of the tool and the workpiece when you are performing the finishing. We have seen in the earlier lectures in introductory part the processes like abrasive flow machining or magnetorheological finishing, all the parts of the components being finished and the tool finishing those components, that particular component are in contact, controlled by load and relative speed. You have to control the load acting on the tool and relative speed between the tool and the, all of them are going to affect the final surface roughness value. Self correcting, higher peaks on both lead to higher material removal rate, both means here tool as well as the workpiece, that also makes the difference in the material removal rate. And there are various processes that we have already seen like magnetorheological finishing, abrasive flow finishing, magnetic abrasive finishing and so on. In optical polishing technique has certain characteristics. Area coveraging process here, as I have just mentioned, that total area of the workpiece surface being finished is covered in one go, whole area is finished in one go. Force controlled process, in all these processes like AFM, MRF and so on, force acting on the workpiece through the medium and through the tool, that control the performance of the process. And then you have random process, abrasive particles distribution is very random. It is not something like turning on lathe machine where fixed tool is there, one single tool is there, or milling where fixed cutters are there. Here cutting tools, they are the abrasives normally and they are randomly distributed in the medium. And then large number of parameters are there which control the process performance. Just like if you take the AF, abrasive flow finishing process, you have the medium composition, percentage of the abrasive particles, the force that is acting over there, the relative speed within the abrasive particles and the workpiece and so on. So, large number of parameters that control the performance of the process. It is slow, definitely finishing rate is comparatively very slow if you compare it with the say diamond turn finishing. It is tedious and skill dependent process, and high level of finish can be obtained, even sub nano level of surface finish can be obtained with a new process developed at IIT Kanpur, chemo-mechanical magnetorheological abrasive flow finishing process. We were able to achieve 0.456 nanometer, that is 4.56 angstrom surface finish on the single crystal silicon wafer. And form control on simple geometries is comparatively difficult as compared to other category of the finishing technique that we will discuss after this slide. And machines are not accurate, or the finishing process is not deterministic, because here abrasive particles are randomly distributed and process is being controlled by various input parameters. So, it is not deterministic process. Then another category of finishing techniques is the deterministic machining techniques, and they come in the category of hard loop finishing techniques. Now, diamond turn machining is the one which comes under hard loop finishing techniques, and the kind of the surface you obtain in diamond turn machining is in the category of finished surface. Now, path is controlled process, path controlled process, Here you are able to control the path of the cutting tool with respect to the workpiece by having relative motions between the two, and it is a path control process. It is deterministic in nature, because you know the relative motion between the tool and the workpiece. You can control the relative motion, you can control the forces through different depth of cut and also the feed rate, hence it is known as deterministic process. Then there are few number of parameters only, not very large number of parameters as in case of soft loop finishing techniques. And here in this particular case you can have the parameters like speed, tool signature, that means nomenclature or various angles of the feed, depth of cut and so on. Then it is comparatively very fast and simple process, and you can achieve high level of finish, form and size control. It depends on the rigidity of the machine, especially the vibrations. If vibrations are not there or they are minimized, then definitely you can control the movement of the tool on the workpiece, and that affects the surface finish to a large extent. And then accuracy of the machine is reflected on the product. Whatever is the accuracy of the machine, different parts of the machine, just like the spindle, beds, cutting tools, etc., etc., they affect the final accuracy of the component being machined and finished. Just like slide wedge, centering resolution, whatever is the centering resolution, it is finally going to affect the dimensions being achieved on the machine component. And axis movement, x axis movement resolution, y axis movement resolution, because it is going to decide the dimensions of the machine surface, etc. Now the question is, what is the mechanism of material removal in macro and meso machining? In conventional machining we know ductile material and sliding card analogy is there. It was proposed by Pipes-Senin and later on supported by Merchant and other researchers. So it is just like a playing card moving one above the other. In the same way the material is being removed in case of conventional machining of the ductile materials. But in case of brittle materials, the mechanism of material removal is very different. It is a kind of Hertzian cone, crack propagation, micro nano cracks are formed, and when these cracks join each other they propagate further and the material is removed, and that material is removed in the form of micro nano shifts. So the mechanism of material removal in ductile material and brittle material is completely different. In case of non-conventional machining processes, which we have seen in the introductory 4 lectures, mechanical type, non-conventional machining processes or advanced machining processes, you have the mechanical force and kinetic energy which was removing the material, just like abrasive jet machining, abrasive water jet machining, the kinetic energy of the abrasive particle was responsible to remove the material. In case of thermal advanced micro machining processes, if you recall, melting and vaporization by the basic mechanism of removal of the material. Material was melted, part of it might evaporate also, vaporize also, and combining these two mechanisms the material is removed in case of thermal micro machining processes, just like electric discharge micro machining, laser beam micro machining, electron beam micro machining and so on. And there was a third category, that is chemical dissolution. In this case the agent comes in contact with the workpiece surface and chemically reacts it and removes the material, while in case of electrochemical micro machining it is just reverse of what is done in electroplating. And electroplating, you are depositing the material, in electrochemical machining you are removing the material and you are giving shape and desired size to the component being machined. And there are other types of micro machining processes also which I have not discussed in the introductory lecture. They come under the category of biochemical machining. Biochemical machining is very interesting and very latest phenomena of machining, and if time permits at the end of this course I will discuss it. Then you have the material removal in macro nano machining. Engineering materials, as I have mentioned to you, you can classify them in ductile and brittle materials, and also polymers are there, another category, ceramics are there. So, you have the metals, polymer, ceramics, and I am not discussing here composite materials or other types of the materials as such. So, tool based machining, beam thermal energy based machining, chemical electrochemical machining, that we have already just seen. So, why I am repeating them here is that most of these materials can be machined by one of these processes depending upon the characteristic of the workpiece material. You have to choose the desired micro machining process. Just for example, I can tell you, just like in case of ceramics which are electrically non-conducting, or polymers which are electrically non-conducting, you may have to go for mechanical type of micro machining methods or chemical type of micro machining methods. You cannot use in general thermal type of micro machining methods or electrochemical type of micro machining methods, because they are electrically non-conducting materials. Now, you can see here very interesting phenomena, distribution of defects in the materials. Now, here cavity is the defect, grain boundaries are there, and it shows, it gives some idea of the size of the grains. Now, you can see multi-grain ductile or brittle processing can be done. Now, breakdown of ductile material due to shear slip occurring at a weak point at grain boundary. Shear slip will take place when you are applying the force in this direction or in this direction, slip will take place at the boundaries. But you can see here defects are there. So, the actual strength of the workpiece material goes down substantially due to the defects. I will show you in the next slide also other kind of the defects. So, actual strength of the material is not reflected when you are machining as bulk material in case of macro machining. So, weak point at a grain point you get the shear slip. In brittle materials, the breakdown is due to brittle fracture from cracks around the grain boundaries. When you are applying the normal force over here, cracks develop from the grain boundary, they propagate from the grain boundary, and when two or more than two cracks join together, it becomes larger, and you are able to remove the material in the form of the micro nano chips. You will see it in detail later on. The specific cutting energy is something like 10 raised to power 3 joules per cubic centimeter. Now, atomic cluster or nanometer processing. Now, you can see here very interesting phenomena. This is the vacancy which we saw in the earlier case also. This is the interstitial atom, which is not the atom related to the parent material, and you can have the dislocations. Lattice structure is shown over here. Now, atomic cluster or nanometer processing, you can have the point defect which range from 1 nanometer to 0.1 micrometer. Resisting shear stress become so large at the tool edge to initiate breakage through point defects, that is overcoming atomic bonding force. Now, what happens when you are applying the force in this particular case, since it is a very small of few microns, and when you are cutting it or even less than a micron, when you are cutting this, then you are really shearing or resisting the bonding energy or bonding force of the two or the surrounding atoms, and that is very large. However, in that case, if you see here, you have the defects like interstitial defect, vacancy, etc. And so, the shearing or cutting of the material takes place along these defects. If you go still lower in the dimensions of the removal of the material, the strength becomes too high and it really becomes difficult to machine. But at that point of time, even the brittle material can be sheared just like a ductile material. Let us see. The specific cutting energy in this particular case becomes 10⁴ to 10⁵ joules per cubic centimeter. Sorry, in the earlier case, if you recollect, it was just 10⁻³ joules per cubic centimeter. So, what I am trying to tell is that as you keep reducing the size of the material which you are going to remove in terms of micro or nanometer, then the strength of the workpiece material goes up and it becomes more and more difficult to cut it. So, you can see you may be familiar with this particular mechanism. This is the single point cutting. These are the different grains of the workpiece material shown over there. When you are applying the cutting force in this direction and tangential force in this particular direction, it is cutting the grains through the grains, as you can see over here, and this is the depth of cut. Step of grain boundary is over here, crystals you can see here. Now, different kinds of defects reduce the strength of material in bulk and removal in macro meso machining. So, that is why, and this angle when you are cutting it is known as shear angle, and this is the shear strength of the workpiece material. Now, you can see here you are not shown the crystals etc., only the bulk material is shown over here, and this is the kind of the cutting single point cutting tool normally used. Now, here when you are applying the force, shear force and cutting force, you can see this is the plowing force, like here red color. Resultant force without plowing force is shown here in yellow color, and this is the resultant force shown in blue color. Now, this is the damaged layer over there, this is the depth of cut, and this is the chip being formed, and various angles etc. we will see in the following slides. And this is the mechanism of cutting of bulk material as well as a small amount of material with the help of a single point cutting tool. Burnishing and elastic recovery are considered. We will see what is the burnishing and elastic recovery. You understand, when there is no removal of material, just deformation, elastic deformation takes place, and which is recovered after you remove the forces. And plowing force is significant in this particular case. Elastic recovery causes interference at the clearance surface, and this is the clearance surface. Because of elastic recovery, this material comes in contact with the cutting tool flank face, and additional friction is developed over here, apart from what is happening in the primary shear deformation zone and secondary shear deformation zone. This also generates the heat energy, and which raises the temperature of the cutting tool as well as the workpiece and the chip. Now, plowing force is there, as you can see over here, and these are the same kind of the structure shown over here, except that the force direction is shown over there. And here this is the rake face of the tool. When the chip is moving on the rake face of the tool, secondary shear deformation takes place, which generates the heat, and it raises the temperature of the cutting tool. Once the temperature of the cutting tool raises, definitely strength of the cutting tool reduces. And you can see here this portion, work tool interface, which is not a desirable one, but due to the elastic recovery and improper design of the cutting tool nomenclature, this kind of interaction takes place, and you can call it as tertiary shear deformation zone, where again due to the frictional forces between the cutting tool and the workpiece surface, heat is generated, and it further raises the temperature of the cutting tool and the workpiece. So, plowing force is not due to chip formation, but due to blunt edge, and this is the edge, right, and you can see the radius of the edge also. Significant when depth of cut is small, this plowing force becomes significant if depth of cut is small. Now, there are three possible ways of tool workpiece interaction. You can clearly see here is the rubbing. That means no material is being removed, only the frictional force is there, heat is generated and tool is moving over the workpiece. Then there is a burnishing, some deformation is there, elastic deformation mainly is there and plastic deformation is almost minimum and burnishing is taking place, but surface characteristics change to some extent in this particular case. And in case of cutting, the material is being removed in the form of the chip, as you can see here. This is the chip formation, this is the workpiece material and this is the cutting tool. So, you can have three cases like rubbing, burnishing and cutting. Mostly we are interested in cutting, not in rubbing and burnishing in general. So, minimum depth of cut is required for the purpose of cutting. If the depth of cut is smaller than the minimum depth of cut required or critical depth of cut required, then you may end up either with burnishing or with rubbing. And rubbing or burnishing takes place when depth of cut is less than threshold value. In cutting, material is removed in the form of micro, nano or macro chips. Now, here it is very important diagram to understand. As you can see here, this is the resisting shear stress in the workpiece material over here, and this is the chip thickness in micron, or you can say correlated with the depth of cut. Now, you can see here, as this chip thickness is smaller and smaller, this is 500 micron, this is 0.5 micron. As you can see, as the chip thickness is decreasing, the resisting shear stress in the workpiece is also increasing, or its strength is increasing. That is why I was telling you few minutes back that as you decrease the chip thickness, right, then the strength of the workpiece material goes very high, and then you need very high resisting forces, especially when you are machining it in this particular zone. And when you are machining in this particular zone, you are able to machine even brittle material as ductile material, because at that point of time, as I showed you in the earlier slide, you are really cutting a kind of atomic structure. So, as chip thickness decreases, the shear stress increases tremendously, that is shown over here. As chip thickness decreases, it cuts the defect free material, hence very high forces are needed and starts behaving as a ductile material, that I showed you in the earlier slide, that the chip thickness decreases, number of the defects coming across the tool are minimized or reduced, and first elastic deformation, then plastic deformation and then micro cracks are generated in case of brittle material, and with a small tip radius and depth of cut machine under plastic deformation regime only. That is what I told you, if that chip thickness is smaller than critical chip thickness, then you are machining the material under the ductile regime rather than as a brittle material. And that is why in case of diamond thread machining, mostly you are machining it into ductile regime rather than brittle regime. Now, you can see here different kinds of the features of the chip being formed are shown over there. You can see this is the depth of damage in this particular case, DC is there, critical chip thickness. If the chip thickness is smaller than this in this direction, you further increase the resisting shear stress of the workpiece material. Micro fracture damage zone over there and at shoulder is there. Now, see it carefully, the brittle material being removed, as I told you, it is the analogy of the cutting or forming the play cards. So, these are the kind of the chips obtained which are very similar to ductile material machining rather than brittle material machining. You can see a smaller part, again just like a playing cards kind moving over one another, and this is the enlarged view of one of the chips, and this is a kind of continuous chips that you get when you are machining a ductile material you get the continuous chip, but serrated continuous chips, and that is the kind of the chip taken from here, you can clearly see it. So, you can say with the help of these 3 figures on the right hand side that when depth of cut is smaller than or near to the critical depth of cut, then you are able to machine the workpiece material, machine the workpiece brittle material in the ductile regime. So, YC should not go beyond the plane of cut surface to avoid cracking. Ductile regime machine, again machining of brittle material, threshold depth or critical depth is few nanometers only, not even few micrometers. Machining by single tool, that is what you do in case of diamond turn machining. Machining by grinding also can be done, and plastic behavior in ductile regime is obtained as we have already seen in the 3 photographs of the earlier slide on the right hand side. Then ductile regime machining of polysilicon by diamond turn machining. These are the experiments that were conducted by the group of Dr. Bala Subramaniam and others at Bhabha Atomic Research Center, Mumbai, India. You can see very interesting surface finish photographs. They had the feed per revolution is 250 nanometer. This is the original surface that they started machining, and if you see here they had the 13.6249 nanometer root mean square value of the surface finish in the beginning, and after polishing it, polished single crystal silicon by ductile regime machining of the commercial grade, and you can see the difference between this surface texture and this surface texture, and these are the intermediate surface texture. Here the surface roughness value obtained is 0.157921 nanometer. That means it has reduced by more than 100 times, and this is what you obtain by diamond turn machining using the machining of polysilicon components. Now, when you are performing the diamond turn machining, you have the single point diamond tool, and this tool has certain nomenclature, and you have to be careful to maintain proper tool nomenclature before using it. So, you can see here this is the diamond and this is the steel shank. Shank is made of steel, but the tip at the corner is that of diamond, and this is the supporting part over there. Diamond is shown over here. Now, this is again the diamond shown over the top view of the tool, and you can see this is the controlled waviness on the tool. This is the H, right. So, what is the waviness? This waviness should be controlled properly, otherwise lot of vibrations will be there and you will damage the surface of the workpiece being finished. So, it should not have uncontrolled waviness like this, rather it should have the controlled waviness like this as far as possible. So, you can see different angles over here. Here is the rake face having the 0 degree rake angle, this is the clearance angle and again this is the note the top face, and this is the clearance angle shown in other view. Now, suitability of single crystal diamond tools. Crystalline structure enables very sharp cutting edge to be produced. High thermal conductivity, diamond has got very high thermal conductivity. It is claimed it has highest of any material at room temperature. Ability to retain high strength at high temperature, because most of the materials they get softened at very high temperature, but diamond does not matter much if the temperature is high, it is able to retain its hardness, and it has high elastic and shear moduli, reduced deformation during machining, because large force is acting on the diamond tool. So, it should not deform elastically or plastically, otherwise the characteristics of the machine surface will change. Mono diamond crystal orientation, because let us see the orientation of the different faces. You can see this is the octahedral point. Now, along 100 plane, it is easy polishing direction. 110 crystal face, it is very difficult to polish. So, one has to set the direction of polishing very clearly, and 111 plane is cleavage plane, easy to break. So, one has to avoid this particular plane to use. Polishing should be done parallel to bonding direction. You can see here, this is the diamond 110 plane flank face. Now, as in case of single point turning tools, you have different faces of the diamond tool. You have all the 6 angles, that is back rake angle, side rake angle, front clearance angle, front clearance angle, side clearance angle, side cutting edge angle, end cutting edge angle, and nose radius. All of them have to be defined properly before using the diamond tool, also keeping in view the properties of the diamond compared to the cutting tools used normally on lathe machine. Now, weight of diamond is around 0.5 to 1 carat, as 200 to 200 milligram. Now, indigenous monocrystal diamond tool development by certain researchers. Now, here you can see clearly that there are different shapes of the shank of the cutting tool, and these are the diamond tools, and this is the shank, and you can see different shapes of the diamond tool are there in all the 9 pictures, and size of the diamond tool also can be varied because it is very expensive. So, scientists, researchers and users have tried to make as small size of the diamond cutting tool as possible, because they also many times fail. So, you lose them and they are quite expensive. Tool features measurement, orientation of the plane, as I have just told you, as 111, 100 and so on, and then cutting edge radius, which I have shown to you, just like the cutting edge radius like this. This is very important, and it controls the surface roughness value that you are going to achieve, because this radius really generates the surface texture on the workpiece which is being machined or finished by this particular tool. Then you have cutting edge waviness, that also I have shown to you in the earlier slides, and that makes a lot of difference in terms of characteristics of the surface generated, and it is also responsible for creating the vibrations in the machine tool, and if vibrations are there, tool may break and surface may get damaged. So, there should be the minimum waviness on the cutting edge, and cutting edge sharpness definitely controls the forces as well as the surface finish. Now, you can see measurement of cutting edge sharpness, atomic force microscope image of the tool, indentation on the copper, tool has been indented on the copper. Now, you can see clearly cutting edge, these are the other faces, and this is the depth of the or height of the diamond cutting tool. So, all this has to be measured and maintained accurately before really putting the tool or mounting the tool on the shank and using it. So, depth of indentation around 500 nanometer over here, and this photograph was taken by Dr. Kishore of Bark, Mumbai. Materials that can be diamond turned, this is very important to understand that all materials cannot be machined on diamond turned machining machine, especially the ferrous materials have lot of problems while machining them. So, the semiconductors that can be machined are like given here: gallium, cadmium, germanium, lithium, silicon, zinc and zinc sulfide. The metals which can be machined are aluminum and alloys, copper and alloys, electroless, nickel, gold, magnesium, silver, zinc. And then the plastic, acrylic, fluoroplastics, nylon, polycarbonate, PMMA, propylene and styrene. So, these are the different kind of the materials which include semiconductors, metals and non-metals, and they can be easily machined. But you do not find here the ferrous metals because they have problems. Iron interacts with the diamond, hence ferrous metal cannot be easily machined by this particular process. Now, let us see some details about the diamond turning machine. These are the ultra precision machines because they deal with the nano level of machining. So, machine accuracy is better than CMM, that is coordinate measuring machine. Secondly, spindle run out should be less than 50 nanometer. Volumetric error zone is few tenths of cubic nanometer, that is like that. Single crystal diamond tools for non-ferrous materials. Natural diamond for 120-degree cutting arc, it is similar to nose angle, cutting a nose angle, which I have shown to you in the earlier slides. Then synthetic diamond for greater than 120-degree cutting arc and cutting sharpness around 5 nanometer, and CVN tools for ferrous materials. As I just mentioned, that diamond tools are normally not recommended for ferrous materials, hence cubic boron nitride tools are commonly used for ferrous materials if required for that particular purpose. So, requirement of DTM, this is very important, especially the characteristics required on diamond turned machining machine. Important design features of DTM machine are machine base stiffness and stability, both are very important, because if it is not stable and vibrations are there, it will definitely damage the machine workpiece and you may not get the desired features on the machine workpiece and surface roughness value. Smooth spindle motion should be smooth, it should be accurate, and you should have the repeatability as long as this motion is concerned of the spindle. Now, you have smooth slide motion, you have X, Y slides or X slides and Z axis movements. So, they should be smooth. If smooth is not there, then jerk will be there, vibrations will be there, which will affect the accuracy of the machine surface, and it will not give you the repeatable result, that is very important. And then servo motors are used to control various motions of different parts. Positioning accuracy is another very important aspect. If you have not positioned accurately the workpiece or the tool, then in both cases the dimensional accuracy will be affected and you will not get the right kind of the component. And vibration control is extremely important, because this is going to affect the final qualities or the characteristics of the machine component. Definitely temperature control is important, as in case of conventional machining machine also, because if temperature is high, it is going to affect the properties of the workpiece material as well as the cutting tool, and both are undesirable. And then you need measurement system online if possible, so that you can check whether the dimensions that you want or the surface finish that you are expecting are obtained or not. Otherwise, if they are not obtained, in many machines you can make online corrections to achieve the desired results. And tool quality and accuracy is again important, because this is the tool which is going to control the characteristics of the machine surface. Then some characteristics of the DTM machine for the spindle system, which is very important. it is designed to overcome the effects of friction, wear, heat and vibration. All of them are going to really affect. Friction is going to affect the cutting forces, and cutting forces will affect the vibrations if any. Then wear of the cutting tool is going to affect the machine surface characteristics, and the wear of the tool takes place as you find in single point turning tool and others. And then heat, as I have just mentioned, vibration I have also mentioned, that all of them are going to affect the characteristics of the machine component as well as performance of machining. Then you are using aerostatic bearing, extensively used in diamond turned machining machine to minimize the vibration, friction both, and minimize air turbulence in the bearing by proper design, so that the performance of the cutting is not affected. Spindle drive is another important device. It is quite popular, and integral spindle type brushless DC motors are used for spindle drive purposes. Then workpiece and tool positioning system both are very important, because if they are not positioned properly, either workpiece or tool, then final results will not be as you want. So, it includes table slide base, table drive, feedback system, tool post and tool. So, all of them will affect the performance of the machining, diamond turn machining. Machine support system are there, machine base and vibration insulator, both of them are going to affect the vibration generated during machining. The machine base should be strong enough and it should have vibration insulators, so that vibrations do not generate and they do not affect the quality of the machine component. Tool measurement system, it is important to know the following to get proper accuracy, tolerances and precision. All the three are very important: accuracy, tolerances achieved and the precision. X and Z offset, x axis and z axis offset values of the cutting tool, tool nose radius, they should be known in advance, so that you can set rest of the things, because if you know the tool nose radius, then only you can predict what is going to be the surface finish, because surface finish is controlled by the tool nose radius as well as the feed rate. Then position of the center of the tool nose radius, if it is not positioned correctly at the center, then final results may not be as you expect. Tool center height is another parameter which affects the overall performance, and waviness of the cutting edge, that also we have already discussed. To achieve above features or qualities in the DTM machine, following technologies have been implemented by the manufacturer, because all these characteristics that are shown over here that you achieve, you need certain technologies, certain devices, so that they can control all these things. So, for that purpose, following technologies have been implemented by the DTM machine manufacturer. Vibration isolators are there, then monolithic granite bed for machine table, because strength of the machine base is very important. So, normally they use monolithic granite bed for that particular purpose. You have hydrostatic bearing for tables, aerostatic bearing for spindle, and then linear scales, laser scales and feedback system. Then you have the linear motors, you have the online or on machine tool measurement techniques. This is again very important, as I just mentioned to you, so that you can know what is happening during machining. Then you have very high stiffness of the tool post, because if the tool post is not stiff enough, then it may generate vibrations and it may lead to the premature failure of the cutting tool, and that is very important. So, the stiffness of the tool post should be taken care of properly, and then you have the vacuum clamping. So, these are the some of the technologies which are being implemented by the DTM machine manufacturer to attain the characteristics of the DTM machine mentioned in the earlier slide. And I am not going to discuss the details of these technologies being implemented. It is not a really a part of this particular course. You can find them in the book published by Dr. Bala and his colleague on the diamond turn machining machine, and it was published by the CRC Press USA. You can see, I will show you some of the pictures which will give you an overview from outside how all these machines look like. So, this is a diamond turning lathe, pictorial view of DTM. You can see screen etc., all the things are covered from outside. Once the machine starts, all these doors are closed and then only machining starts over there. You have DTM bed, as I was telling you, monolithic granite bed. This is quite heavy and very neat and clean and very accurate bed is maintained, because on this accuracy the machining accuracy is concerned, is controlled, and you have the air isolators also at the bottom of this, so that vibrations are not transferred to the machine. You can see the DTM details are there. Here you can clearly see the cutting tool, the workpiece being turned and other features of the machine. Here more detail, this is the cutting tool, workpiece can be held over here, and air cooled spindle with the integral motor. You can use the linear motor over here, and hydrostatic slides are there. Now, it clearly shows the tool which is having the diamond tip over here, rest of it is the shank made of metal, and this is the tool shank holder. Servo, fast tool servo is used. Again you can see optical tool measuring system, as I told you that you need online measurement system. So, when you want to check different nomenclature of the cutting tool, you can use this kind of the optical tool measuring system, and you can check whether the tool has been or the diamond tool has been prepared properly or not, because that is what is going to affect the performance as well as the quality of the workpiece being machined. Now, there are various applications of this particular process, like spherical and aspherical, ophthalmic lenses, medical instrumentation, micro laser, optical disc, CD players etc., where you can use this particular process, aluminum scanner mirror, space communication, high power machining laser optics, mirrors for X-ray telescope, where you can have these components made by this particular diamond turn machining machine, infrared hybrid lenses for thermal imaging system. Now, these are the actual photographs of some of the components which I have used diamond turn machining machine. You can clearly see, and you can see the reflection of from the surface which has been machined. Now, you can again see the kind of the components which have been machined over this particular surface. This is the 2D line diagram of the components machined by this particular process. This is nothing but the line diagram of these components. Present application at work: ultra precision bearing, one of special material ball bearings, metal mirrors, accelerator cavities, and optoelectronic components. They have been made using this particular process. Now, this is very important applications, just like a mirror being finished with this particular process, and X-ray diffraction images are there in this particular case, as you can clearly see. Metrology for DTM, component measurement, dimensional measurements, form, surface finish. So, you have to measure all these things online and offline also. You can check it and decide whether the machining has been done properly or not. Then tool features measurement is there, cutting edge radius size we have already discussed it, cutting edge waviness also we have discussed it. So, all these things you can use metrology for measurement and checking whether they are correctly made or not. And then online tool measurement for offsets, where how much is the offset x and in x axis and z axis, and they should be corrected before really you start machining it. Whether you are at shop floor or top floor, means manager or general manager, does not matter. Really what is more important, you should always keep in mind that you cannot design a part if you cannot manufacture it. I will just explain it. Suppose some designer says you make a part of so many nanometer and you do not have the facility or those kind of the machines are not available, definitely the design is of no use. And same way you cannot manufacture a part if you cannot measure it. When, as I just told you in this particular lecture, that you are making it and you are getting say surface roughness of 2 nanometer RA value, but if you cannot measure it, you really do not know whether it is 2 nanometer or 200 nanometer, and if you cannot decide this, then really there is no sense in saying that I have made this particular part. So, you cannot manufacture a part if you cannot measure, it is equally true. So, these two things you should keep in mind. Quickly I will show you dimension measurement with the help of CMM machine. You can see it, error zone of CMM metrological zone is 0.8 micrometer cube, error zone of DTM metrological zone is 50 nanometer cube. So, you can see the difference between the CMM machine and the DTM metrological measurements and DTM capabilities, right. So, and here is the CMM machine which can be used for the measurement of some of the features of the machine component. So, you can use this DTM component, you can measure for measurement with the help of the profilometer, that is telesurf, and phase shift interferometer devices can be used for the measurement of certain features of the machine component. This is the another device which is used for the purpose of measurement, profilometer, telesurf profilometer, very expensive machine, but very useful machine. As you can see here, pin is there with the help of which you can measure the features on this particular component, and whatever feature you are measuring, here you can see the surface finish pictures are given over there. You can see it on the screen, and the values are given over there which are not visible right now. So, with the help of those values you can decide whether you have achieved what you are looking for. So, you can see the contact type, non-contact type, two types of these devices are there. One is this is the contact type device. You can also have non-contact type device just like a microscope, and you can have 5 to 10 nanometer resolution, 3D topography can be obtained, 2D micrographs can be obtained, and you can measure the surface finish also with the help of this telesurf device. This is the 2D picture of the surface roughness that has been obtained with the help of the telesurf. Now, these are the different values you can see here. As I told you, you normally measure RA value, RQ value, RC value, RY value, and so on. So many types of the surface roughness can be expressed in different ways, because different countries use different ways to express the surface roughness. Now, you can clearly see here that this is the CNC turned surface. What is the texture of the turned surface with the help of the CNC machine, and this is the DTM turned surface, and you can clearly see the difference in the texture of these two types of the turned surfaces. So, it clearly tells you the quality of the turned surface on the DTM, and this I will just show you the kind of the surface finish you are obtaining in different operations. Like DTM, you can see clearly what a good surface finish is obtained. This is a CNC turning surface, and this is the grinding surface, and this is the CNC milling, and this is the EDM electric discharge machining surface, electrochemical machining and chemical etching and turned plus lapped surface. So, you can clearly tell that DTM is giving the best surface roughness value as compared to all other existing processes which I have just mentioned over here, including the lapping. So, this photograph or pictures have been taken from the paper on the conference on precision engineering, that is the COPEN 2005 by Dr. R. Balasubramaniam, Tarun and Dr. V.K. Suri. And this is the interferometer with the help of which you can measure different characteristics of the machine component. Measurement of the form accuracies to optical wavelength resolutions. And this is the application, one of the applications of diamond turn machining. This is the mirror which has been finished for space applications, astronomical telescope mirror, as you can see here, which is used by the BARC, Bhava Atomic Research Center, and this kind of this is the mirror for that, and this is the kind of the another mirror, and this has lot of applications in the photocopying machine drum also, and high speed bearings. Conclusions: DTM as a nano machining process is well established in India. Indigenous single crystal diamond tools are developed. Metrology for DTM is established. Scope for research, lot of scope is there for the researchers to work in, just like experimental studies, material removal mechanism, molecular dynamic simulation can be, lot of work can be done in this direction, and there are so many applications in industry and scope for industry like product manufacturing, machine development and development of metrological instrument. Thus, we can see that DTM has lot of applications on the research front as well as industrial front. Thank you very much. Thank you.